Okay, right, so what does it mean by a proof or a certificate that a system of linear inequations like this has no solution? Well, suppose this was your input instance, and I suppose I just told you, hey, add up all these inequalities. You know, if there's a solution to all these inequalities, then that solution X should also satisfy the sum of the inequalities. And imagine, like, by some weird miracle, when you just formally add up the left-hand sides, like all the coefficient sums add up to 0, the left-hand side cancels out completely. You get 0 on the left-hand side, and the right-hand side adds up to like the number 1 or some other positive number. Okay, then that would show that no matter what X is, if it satisfies all these inequalities, it would also satisfy their sum. And in this miraculous setting, the sum is 0 greater than or equal to 1, which is, you know, not true. And that would be a proof, or that would be like a demonstration that these inequalities have no solution. You can generalize this a bit. More generally, you know, if you have an inequality, you can always multiply it by a non-negative number lambda, and it'll remain equivalent. And suppose I pointed out some non-negative multipliers, lambda 1 through lambda m, and you know, you multiply the inequalities up with these numbers, lambda 1 through lambda m, and added them up, and then the miraculous thing happened, which maybe is less miraculous if you choose these lambdas carefully, that everything on the left-hand side cancels out, and everything on the right-hand side becomes the constant 1. Okay, this would be also demonstrating that there's no solution to these inequalities. And this is the kind of proof of unsatisfiability that we're going to be talking about for linear programs. Right, so you'll multiply each of these inequalities by lambdas that are non-negative, and then you'll add them all up, and all the coefficients will come out to 0 on the left-hand side, and on the right-hand side, you'll get the number 1. So let me do something here. Okay. Great. So if such lambdas existed whenever the system was unsatisfiable, then it would mean you have like a cool, succinct way to prove that unsatisfiable systems are unsatisfiable. And this always happens. And this is the content of what's called the Farkas Lemma, or it's basically the same thing as LP duality. And it's this theorem, which I'll show to you, that whenever a list of inequations has no solution, so the K that they define is the empty set, there is a proof of this sort. These non-negative lambdas, which when you multiply them against the inequations and add them up, they give 0 greater than or equal to 1. Such lambdas always exist. Okay, and this was proved by Farkas in 1898, basically also proved by Gärtner in 1873, but somehow he never gets the credit. He's actually probably most famous for being Emmy Noether's PhD advisor these days. Okay, I'm getting a question here. Let me check it out on chat. The question is, does that mean that if all the coefficients on x1 were positive, it's always satisfiable? Yeah, that's exactly true. So it is true that if all these coefficients on x1 are positive, then it's always satisfiable. And the reason is, you have a solution where you just set, let's say, x2 through xn all to 0, and then set x1 to be some enormous number, positive number, big enough so that it would exceed all the right-hand sides b1 through bm. Okay, so this relies on the fact that, you know, our inequations are all of this form. They all have greater than or equal to signs. Does that make sense? Okay, good. Cool. Good question. All right. And this also, by the way, this was known in like the 50s and stuff and 40s. And basically, if you ignore these things about bit complexity, it tells you that, you know, obviously if a list of inequations has a solution, then, you know, you can just show the solution X. And so that proves that linear programming is an NP. And this also, Farkas Lemma also implies that when there is no solution, you can just show these lambdas, and it's sort of a witness or a certificate that there is no solution. So people knew all along that linear programming was in NP intersect co-NP, if you remember this complexity theory stuff. And that kind of hinted that it was perhaps just in polynomial time solvable in P, which indeed proved to be true. Okay, so I'm going to show you a proof of the Farkas Lemma. This is sort of a proof by example. And the proof uses this thing called the Fourier Motzkin elimination algorithm, which in a sense is an algorithm for solving linear programming, but as we'll see, it's like an extremely inefficient algorithm, but it's an algorithm that is useful for theoretical reasoning. Good. So let's suppose this is your input. There's just 3 variables here. So instead of x1, x2, x3, I'll call them x, y, and z. And so you have these 5 inequalities. Okay, and we're going to try to reason about whether or not they're simultaneously satisfiable. So just like you're taught in high school or whenever to solve systems of linear equations by this technique of first eliminate the first variable, then eliminate the second variable, then eliminate the third variable, you can also do that with linear inequalities, and that's what Fourier Motzkin elimination does. So the step 1 is to somehow take this system of linear inequations and find another system that doesn't involve x at all and whose satisfiability status is the same as the satisfiability status of the original system. So how are you going to eliminate x? So let me tell you. First thing you do is you multiply all the inequalities by positive constants so as to make the coefficient in front of x either +1 or -1. Okay, so whenever x had a +1 or a positive coefficient before, it's going to have a +1 coefficient here on the new set. And whenever it had a -1 coefficient before, or sorry, a negative coefficient before, it's going to have a -1 coefficient on x in the new set. Okay, so that's easy, and it doesn't change the set of solutions, in fact. Now, don't change the inequations at all yet, but mentally think of them as being upper bounds and lower bounds on x. So whenever you have like a positive x, you can think of this as an equation on the left here that's like x is bigger than some stuff involving y and z and constants. And whenever you have an equation whose coefficient on the right is minus, you have minus x, you can think of this, if you move the minus x to the other side and the constant to the left side, you can think of this as an inequation of the form x is less than or equal to some stuff. Great. So, and if you have some inequality in the right system here that doesn't involve x, just like temporarily forget about it for a moment. So we'll just think about what bounds are implied for x here. And now you see it's not too hard to understand. You have some expressions that x is supposed to be bigger than and some expressions that x are supposed to be smaller than. And like, think of y and z. I just put the original system back up there. Think of y and z as numbers. Temporarily think of y and z as numbers, but x is like a variable. And then over here, your constraints on x are then x is bigger than some numbers and x is smaller than some numbers. And you see, there is a legal or an acceptable solution for just the variable x, if and only if all the lower bound numbers are smaller than or equal to all the upper bound numbers. Right, so this thing involving x over here on the left is satisfiable or has a satisfying x if and only if all the lower bounds are smaller than the upper bounds. So we can just kind of take a cross product here of all possible pairs of a lower bound and an upper bound and make a new inequation about it. Okay, so we have the red lower bounds or reddish lower bounds and the greenish upper bounds, and we'll sort of take this cross product. So this is actually going to make a lot of inequations as we do this, but as I mentioned, this algorithm is not efficient. And on the right now here, we have 4 inequations which are satisfiable if and only if this set on the left for a given y and z, they're satisfiable or satisfied if and only if for this guy on the left there exists a satisfying x. Does this make sense? So this is what I said. There's a satisfying x on the left if and only if we have all these upper and lower bounds square with each other. And let me just take them and simplify them, collect all the terms. So I've done that here. You can take my word for it. And now we can just remember the original system we were thinking about. We also had this one inequation that didn't involve x at all. So let's stick it back in. And we've actually done it. We've actually shown that this initial system with the x's is going to be satisfiable if and only if this new system with no x is satisfiable. Okay, so we've successfully eliminated x. Okay, any questions about this? Okay, great. Okay, so obviously the next step is to eliminate y. And I won't go through that whole process again, but I did it. I probably made some numerical errors, but I believe when you eliminate y in this specific example, you get down to just a bunch of inequalities that only involve z. And actually, when you're down to one variable, it's easy to check if it's satisfiable or not, but we can even go like the whole Megillah and eliminate z itself, eliminate the last variable. And when you do that, you get down to just a bunch of inequalities involving numbers, okay? And then it's really easy to check if they're satisfiable or not. You just check, hey, are all the right-hand sides negative? And actually, in this case, they're not. And that implies that the original system was not satisfiable. Okay, but on the other hand, if all the right-hand sides were negative, then that would imply that the original system was satisfiable. So what I've shown you here is a highly inefficient algorithm for deciding the linear programming problem. There's a certificate right there. Well, this is a witness that it's unsatisfiable. Let me also just mention that you can always multiply an inequality by a non-negative number, and it preserves the inequality. So you can always get your final, unsatisfiable equation to be 0 greater than or equal to 1, if you'd like. And now I want to make a key claim. What I want to claim is that every inequality that you generate in this whole Fourier Motzkin elimination algorithm is a non-negative combination of the original inequalities. And in particular, if that's true, then it means even this last one, in the unsatisfiable case, even this last one, 0 greater than or equal to 1, is a non-negative combination of the original inequalities. And that actually is going to prove the Farkas Lemma, right? That's what we're trying to show. When it's unsatisfiable, there's some way to add up the original inequalities with non-negative multipliers to get the blatant contradiction 0 is greater than or equal to 1. And let me just illustrate this claim for you. Well, I mean, I'll kind of go over the steps quite fast. Here was the original system on the left. The first thing we did was multiply the inequalities by positive constants to get like all plus or minus 1 coefficients on x. So that's multiplying them by just non-negative coefficients. And then we eliminated x. And if you think about it, this is the previous version with x. This is the version with x eliminated. And if you think about it, actually, we got all these first 4 inequations here involving y and z by taking just pairwise sums of the plus x inequations and the minus x inequations on the left. Okay, so for example, we got this first one involving y and z by just summing the first inequation with a plus 1 on x and the first inequation with a minus 1 on x. Okay, so that indeed demonstrates that after this elimination step, all the inequations here indeed were non-negative combinations of original inequations. Okay, and then, in the next step, when we eliminate y and get down to z's, just z's, all those just z's inequalities will, be non-negative linear combinations of these inequations here on the right, which in turn were non-negative inequation or multiples of these inequations involving x, y, and z in the original case. So all in all, as you go along, you maintain this invariant that everything is a non-negative linear combination of the original inequations. Okay, does that make sense? Any questions? Okay. Great. So that, in a nutshell, proves this Farkas Lemma, or this LP duality statement. Now, let's make some more observations. Let's go back to this Fourier Motzkin elimination algorithm. Just think about it a little bit more. In fact, I told you this was a good thing to think about when you're trying to reason about what happens when the system is unsatisfiable. You'll eventually be able to make 0 greater than or equal to 1 as the linear combination. But actually, if it is satisfiable, and in the final step you get all down to 0 greater than or equal to some negative numbers, it's an easy exercise to show that actually you can now sort of go back one variable at a time and reconstruct a solution, and in fact a rational solution, because, I don't know, for example, let's say you've inductively done this so far and you have some solution for y and z, and now you just need to figure out how to set x such that all these inequations on the left are satisfied. Well, the way it's set up, right, with these y and z now being numbers, the whole point is that And it being satisfiable means there is a value of x which is between all the upper bounds and the lower bounds. So you can just choose any x that's between these upper bounds and the lower bounds that you've worked out, and that'll be an acceptable setting for the variable x. Okay, so you can inductively build back a solution from the eliminated variables one by one. In particular, that shows that if you start out with rational coefficients, which we always assume, then you can actually get back a rational solution. Okay, so it's a minor comment that there's always a rational solution. Now, as I said, this is a highly inefficient algorithm. It's not the polynomial time algorithm for linear programming. And in particular, you can see if you start out with, like, let's say, m inequalities, you're doing this elimination step, maybe half of them have a positive coefficient and half of them have a negative coefficient. You take, like, the cross product between them, you'll generate m/2 squared inequalities. So even eliminating one variable kind of squares the number of inequalities you have. So if you eliminate n variables, you get a doubly exponential time algorithm, like m to the 2 to the n, okay? Which is, of course, very bad. But we learned some things by thinking about it. We learned the Farkas Lemma. We learned there's always a rational solution when there is a solution. So it's still worth thinking about. Right, so is there a polynomial time algorithm for linear programming? Well, there is, as I mentioned, but we'll get to there in the end after actually maybe 2 lectures from now. But before getting there, we should actually, again, come back to this sort of technical but interesting to me question. Before wondering if there is a polynomial time algorithm, we need to wonder if there are even polynomial bit solutions. Okay, so remember, a solution, when it is feasible, when k is feasible or non-empty, you're looking to find a quote-unquote feasible x, meaning an x that satisfies all the inequalities, or else you want lambdas which prove that x equals the empty set. And here, what do I mean by bit size? Well, remember, we're working with digital computers and, either the word RAM or the Turing machine model. But in any case, every number, you can't work with it by magic. You have to store it. And it's going to be a rational number. So I'm going to use this notation just in this lecture because it's traditional. The bit size of an object, I put in angle brackets, and it's the number of bits needed to encode it in, like, a standard method. Okay, so for an integer, it's the number of, base 2 digits of x. And if it's a rational number, we're just going to store it as, like, a numerator integer and a denominator integer. If it's a vector, then it just means, the sum of the encoding lengths of all the numbers in the vector, same as if it's a matrix, et cetera, et cetera. And an important theorem for linear programming, which is sort of necessary in order to show that there's a polynomial time algorithm for linear programming, is to show that the output that you're looking for, the feasible x, if it is satisfiable, and the proof of infeasibility, if it's not satisfiable, can be written down with polynomially many bits. So luckily, that's true. So here's a theorem that we're going to reason about. It says, let's say you're given a system of inequalities k, and it's traditional in linear programming to write capital L for the number of bits needed to encode k. So this is a number that's like m plus n plus the encoding length of all the numbers in the inequalities. That's L. And it says you're in good shape. So if k is non-empty, there is at least one solution. Then not only is there a rational solution, x, but there's one that you can write down with poly n bits. And if k is the empty set, then there exists a rational proof of these lambdas that also have only polynomial in L many bits. And what is the proof of this? Well, that's what I want to talk about for a little while. First thing I'll say is actually it suffices to show bullet point 1. It suffices to show that when there is a solution, there's a solution with polynomially many bits in it. And what is the reason for this? Well, suppose we knew it was true for bullet point 1, how could we reason about polynomial bit size for the lambdas in the case where it's unsatisfiable? Well, and this is a bit of a detour, but the reason is, once you know it's unsatisfiable, or when you're interested in this, the question of given k, are there lambdas which certify that k is unsatisfiable? This itself is a linear programming problem in the variables lambda. So I'll talk about why that's the case in a moment. But this is called the dual linear program. And this dual linear program in the lambdas, its bit size is about the same as the bit size of your actual system k. And so this is why it suffices to show bullet point number 1, assuming this fact about there being a linear program for the existence of the lambdas. To get bullet point 2, Well, you just use bullet point 1, but applied to the dual linear program about the lambdas, whose bit size is about the same. It's also about L. Okay, so yeah, why is this question of finding the lambdas, certifying unsatisfiability of K, why is it itself a linear program? Well, let's just look back at the Farkas Lemma, which is here. This is our input data, these inequations involving the x's and the a's. And the Farkas Lemma says that if K is empty set, if these are unsatisfiable, there are these non-negative lambdas, which when you multiply them against the inequalities and add everything up, you get 0 greater than or equal to 1. So let's just rearrange this a bit. We're looking for lambdas which are non-negative, which is a good start, right? You're allowed to have these as constraints in a linear program. Think of now the lambdas as the variables, and the x's are kind of going to go away, and the a's are going to remain constants, and the b's are going to remain constants. So yeah, so now if you think about this a little bit more, to say that, let me go back a little bit, to say that the lambdas, when you multiply them against the inequalities and add them up, to say that you get a coefficient of 0 on x1, it's just to say that lambda 1 a11 plus lambda 2 a21 plus dot 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 lambda m plus am1 is equal to 0. And that's encoded by this vector matrix multiplication. That first constraint is saying that this row vector of lambdas times this column vector of a's equals 0. And we want a similar thing for all of the columns. We want the row vector of lambdas times the second column of a's to equal 0, dotted with, I should say. And it should be true for all of the columns. They should equal 0. And then we also want that the dot product of the lambdas with the b's should equal the number 1. So really what we've got here is a bunch of equations on the variables lambda, plus the constraints that the lambdas be non-negative. And this is indeed a valid linear program. And this program is the dual linear program. It's the one about certifying unsatisfiability of the original K. Any questions about this?